Okay, so I think it would be a good idea if we start the lesson. I hope that you enjoyed your holidays. Okay, so we continue as before. So let me go to lights.
Bob, I have a question.
Yes, please.
Will you be our substitute for physics?
Today. Okay, so now let us start this new lesson. So consider n objects and let r a natural number starting. The minimum value for r is 1, the maximum value is n. So n, you have n objects and r is a number from 1 up to n. A permutation of these objects consisting of r of these objects is called an r-permutation of the objects. Yes, so it means, for example, if you have 3 letters, A, B, C, D, 4 letters, you can choose 3 of them and then start arranging them in order. That is called a 3 permutation, yes, of these 4 objects. That's it. And the number of r permutation of n distinct objects is denoted by this symbol. This is the one used in your book, but there are 2 more that you might find in other books as well. So Pn and r is the number of r permutations from n distinct objects. Yes? This is just a terminology that I want you to learn. We had the word permutation before, but now we add r to it, we say r permutation. And the number of permutations for n distinct objects, do you remember it was n factorial? But the number of r permutations of n distinct objects is denoted by this. We still do not have any formulas for that. We will derive that in this lesson. Okay, so let me start with an example. For this vehicle, yes. So write down all 2 permutations of the letters A, B, and C, and D. By counting these permutations, determine P, 4, and 2. Yes? Is that clear? So we have 4 objects, A, B, C, and D. I want to write all possible 2 permutations of them. What does it mean? It means that I have 2 degrees of freedom. 1 degree of freedom is which letters I am choosing, which 2 letters I'm choosing. Another degree of freedom is that how I arrange them. And that's because the word permutation means that the order matters, yes? Okay, so what should we do now? For example, I can choose A and B, but I can arrange them in how many ways? I can write AB, this is 1, 2 permutation. There is still another 2 permutation combined from the same letters, they're composed from the same letters, A, B, and A. Yeah, so these are the 2 permutations that consist of A and B. But of course there are more, yes? I can choose A and C. I can arrange it as A first, C second, or C first and A second. I can still choose A and D, yes? And then I can arrange that as AD or DA. What else? I can choose B and C. I can write it as CB. I can choose BD. I can write DB. And finally, I can write CD and DC. Yes? Is that clear? So these are the only 2 permutations of these 4 objects. Yes? And then if I ask you what is P of 4 and 2, for the time being, we do not have any formulas for this, but we can count them, yes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the answer to this is just simply 12. Is that clear? Yeah? Okay. So remember, but this symbol is meaningful if four objects you have are distinct objects. Yes. Okay, so let us go to the next one. So here the difference is that I have 3 letters A and 2 letters B. Still, I want to write all 2 permutations of these letters. Okay, so what can I write? For example, I can choose to have 2 A's, yes? But in how many ways I can arrange 2 A's? In just one way, so there's only A. I can decide to choose 2 B's, yes?
Yes.
And that's it. But is there any other combination and arrangement that I can have?
AB.
AB, but when it comes to AB, I have another one,
BA.
which is BA. So these are the all possible 2 permutations of these objects, but I cannot use the symbol P 4 and 2 for this case because the objects are not distinct. Is that clear? That's very simple. Okay, now I want to test your opinion about this. What do you expect for this? So let n be a natural number. Determine P, n, and 1. What does it mean? I want you to answer this question based on your previous knowledge. We haven't found a formula for P, n, and r yet. We will derive it later. But you don't need it for answering to these particular cases. So you need to interpret this symbol. What does it mean? It means that you have n objects, n distinct objects, and what you want to do, you want to choose one of them and arrange them. In how many ways you can choose one of these n distinct objects and arrange them? Yes? N. So what you expect is we will confirm that later when we found the formula, but without even that formula, you know that the answer to this should be n. Is that right?
Can you explain that again?
So you have n distinct objects.
Yeah.
So what is let me write it in that way. So when I write P and I write N and R, what do I mean? I mean that I have n distinct objects.
Yeah.
I want to choose R of them and arrange them in a way that order matters for me.
Yeah.
Okay? And this is the number of ways that I can do this. Okay, now I am asking you the same question. When I say P, N, and 1, it means that I have n distinct objects. I want to choose one of them and arrange them in a way that order matters for me. Okay, but when I want to choose one, arrangement is irrelevant here, so the number of choices matters. So how many ways I can do that? Anyways, yes, that's it. Okay, let us guess the other one as well, or at least understand. So what is your answer to this one? What do you think about this? Okay, let us everyone think. Yes? It's n factorial. Yes? Why is that? Because again, I have how many distinct objects? I have n distinct objects. How many of them I want to choose? N of them, and I want to arrange them in a row. So it means essentially that I have n objects, I want to arrange them in a row. In how many ways I could do this? That was the previous lesson, n factorial. So we will confirm that after we found the formula. But you know actually this is true. Any questions? Okay. Now this is the theorem, which is also in the book. So there is a formula for Pn and r. So Pn and r is n factorial divided by n minus r factorial. Okay. We want to have a proof for this. So what is the proof? Why do you think this is correct? So we want to prove that the number of ways that I can choose r objects out of n distinct objects and arrange them in a row in a way that order of the arrangement matters to me is this number. How can I prove this? Okay, so you have n distinct objects. Let me call them object number 1, object number 2, object number 3, and I have up to object number n. And r is a number starting from 1, a natural number from 1 up to n. I want to choose r of these n objects and arrange them in a row in which in a way that order matters for me. So how many locations I need for one r permutation? How many locations I need? R, yes? So let me write, I don't know, location, for example, 1. So let me write, I don't know, location 1, and then I need another location, location number 2, and then let me just do another one, location number 3. I need to fill these up, yes, with these LED objects. So, and then I go up to location number R. Yes, because if I ask you choose R of these objects and arrange them, how many locations you need to fit one R permutation? You need R locations. Okay? But how many choices you have for the first location? In how many ways the location 1 can be filled up? N, because I have n distinct objects. I have this freedom. I choose one of them and put them here. In how many ways I can do it? I can do it in n different ways. Okay, when I do the first one, it means that I chose one of these objects and put it in the first location. And then I go to the next location. How many options are available for me now? n minus 1. And then n minus 2. Okay, now can you tell me how many options will be available for the last rth location?
Is it n minus r?
No, this is usually the mistake that people do, yeah. It's not n minus r. Because you see, the first location is not n minus 1. The second location is not n minus 2. The third location is not n minus 3. So when you say the rth location is n minus r, this is not completely correct. Yes?
Is it then n minus r plus 1?
Plus 1. So that is the number of ways that we can do that. Is that understandable? So this is n minus r, but this plus 1. Is that clear? Okay, but then, so the number of ways that I can do that, which on the one hand is p, n, and r, is equal to what? By the product rule, it is n times n minus 1 times n minus 2 up to times n minus r plus 1. Do you agree? So this is the formula. But this formula can be written more compactly if we use the factorial symbol in a wise way. But this is correct. This is the answer. This is the formula. And I have seen some books write this as the formula. So that's correct. But if I want to use the factorial symbol to write this more compactly, what should I do? I can continue a little bit. So I can rewrite this expression and then start multiplying it by the previous number and then multiply it by the previous number, and I continue this process until I reach to 3, 2, and 1. But I cannot change my problem. I multiplied that. I have to compensate for this change, so I have to divide by this expression as well. Yes, is that understandable what I did? So you see, I multiplied, so that was my expression. I copied and pasted the expression here. I multiplied this by that expression, and I divided by the same expression. So I didn't do any changes at all. So this equality is still valid, yes? But what is the benefit of that? If you look into the numerator, it starts from 1, 2, 3, and it goes 1 by 1 up to n. So what is the number then? So let me write here above. So this becomes just simply n factorial. Yes? And then what is the denominator? The denominator is 1 times the next number 2 times the next number 3 up to times the next number n minus r. So this means this is n minus r factorial. Yes? So this means that this is equal to this expression. So that's the proof. The proof is extremely simple. Yes? And this is why people, sometimes I see that they don't use this formula that often. They start solving problem from scratch every time. That's up to you. That's not a very bad idea, but I myself prefer to write and use the formulas as much as possible. Yes?
Could you explain why they add this 3 through 1?
No, I'm just, no, I added it. So I don't know, this n minus r is some number.
Yeah.
And this number is 1 unit less than this number. I am just, I don't know, for example, assume that this number is 10. And if you subtract 1 at a time,
yeah,
eventually you will reach to 3, 2, and 1. Yes, so that's it, yes? I just wrote them for make it clear. Yeah. So this is the formula which is in the formula sheet. And by the way, if you are using calculator, there is a button on your calculator that calculates this one directly. So you just put 2 inputs there, and you need to find it on your calculator as well. Okay, but let me see this remark now. Okay, before going to the remark, let me ask you again. When do you think we can use this theorem? Let us review this. I use this formula when I have n distinct objects. I want to choose r of them and arrange them in a row in a way that order matters to me. So if I want to count the number of r permutations of n distinct objects in the way that I describe, this is where that I use this formula. Or you can imagine like this. Assume that you have n distinct marbles, but you have only r locations. R is at most n. You want to distribute these marbles into these locations, or let us call them boxes, in a way that every box receives exactly 1 marble. This is the way that we can distribute this. This is the number of ways we can distribute it. Okay, is that clear? So now let us go to this remark. So even though in principle P and R makes sense if n and r are natural numbers, so you see, because this seems a little bit odd. When I say P, n, and 0, you might say, what does it mean? Technically, it should mean I have n distinct objects, then I do not choose any one of them. And I don't know how to interpret that. Yes, because I want to choose 0 of them and arrange them. So you might think that this doesn't make sense, but it actually makes sense. Okay, so if you want to calculate this using the formula, not the interpretation. Interpretation is different from the formula. So if I use the formula n factorial, n minus r factorial, it also makes sense if r is 0. If r is 0, then this is gone. Then I will get n factorial over n factorial, which is exactly equal to 1. So even if you see this, Pn and 0, the answer is 1, even though there is not a good interpretation in the combinatorial form, yes? Okay. And by the way, you already answered that Pn and n is n factorial. Do you remember? But now let us use the formula here, n factorial over n minus r. In this case, r is n factorial. So what do I get? I get n factorial divided by 0 factorial. But what was 0 factorial? 1. And you remember, that was also a convention. So that convention was chosen in a way that we have this consistency here. So here, if I chose 0 factorial to be any other number, then I have to modify this formula. So in order not to modify the formula for the case of r equals to n and r is not equal to n, mathematicians prefer to just adopt this harmless convention that 0 factorial is 1. So that's a good definition, and we have the consistency here. Okay. Now let us try to solve some examples and then we are done. So how many 4-letter words can one construct using the letters in the word keyboards? Okay. So what we have for keyboards, we have K, we have E, we have Y, B, O, A, R, D, S. So the first thing that you need to pay attention to is that all of them are different. And how many of these objects I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 distinct objects. And then I am interested in 4-letter words. So I don't need all of the 9 objects. I need only 4 of them at a time. And then, because in constructing a word, the order of the letters matter, so this is just a permutation problem. Yes? So I just want you to understand. Is that understandable? So then I can just answer the problem as simple as that. I can say P, 9 objects, 4. That's it. So that's the answer. So sometimes I just care about the final answer written in this form. But sometimes I also ask you to calculate the value. So for the practice for this problem, let us calculate the value. So how should I calculate the value? Let me remind you about the formula. So what was the formula? If you have P, N, and R, the answer is N factorial. So the first number factorial appears in the numerator, and the difference between these factorial appears in the denominator. So this is the formula. Okay, so I use it here to answer this question. So this becomes just simply 9 factorial divided by 9 minus 4, whatever it is, factorial. So 9 factorial is just 9 times 8 times 7 times 6 times 5 factorial. Do you agree? Instead of 9 factorial, I can write this, and then 9 minus 4 is also 5, so it becomes 5 factorial. And then 5 factorial, whatever it is, and that one are simplified, and still the number is not that friendly to calculate, yes? Anyway, you can put this in the calculator and get the answer, whatever it is. Okay, and then of course I told you that there is a button on the calculator. You can immediately use that. Yeah, just put it in your calculator and then you get the final answer. But that is not that important. The important thing is that when I am allowed to use this formula to count the number of the desired item in the problem. So do you feel that that is the formula here? Yes? And I really prefer to use the formula. You can of course start from scratch. You can say that, okay, I need a 4 letters, so I have 4 locations. How many ways I can fill this? 9 and 8 and 7 and I don't know, 6, and that's the correct answer. So essentially you don't need that formula, but I want you to learn to use the formula. Any questions? Okay, let us go to the next one. How many 5-digit numbers with distinct digits are there such that each starts and ends with an odd number? Yes? So how should we answer this question? So the number of distinct digits we have is 0, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are the digits that I can use. I want to have 5 digits. So let me just try to understand that. So we need 5 locations. Here and here. Sometimes you have to use the formulas and the product rule together Okay, so what we want to do, the number, the 5-digit number is supposed to start with an odd and ends with an odd number. And the digits should be distinct. Okay, how do you solve the problem now? Don't think that you can immediately use the P formula that we learned today. So you need to use it in combination with what you learned before. So again, that might be you have forgotten. If you want to count the number of items in this problem, try to do it practically. If you want to really do it practically, what do you do first?
Start picking the
Odd numbers in the first. Okay, so just start doing that. In how many ways I can fill up the leftmost digit with an odd number? In how many? 5, yes? So 1, 2, 3, 4, 5. So for the first one, I have, so a stage 1, so let me call this a stage 1. I have 5 options available for a stage 1. But because the digits are supposed to be distinct, I am not allowed to choose this item once more again. So this means that one of these odd numbers, whatever it is gone. And then a stage 2, which one do you prefer to choose a stage 2? The end number. So let me call it the stage 2. Now how many ways I can fill up this stage?
4.
4. Yes, that's also clear. So I put 4 options here. But then another odd number is gone. Okay, so how many numbers in total are left for me? There were 10 of them, 2 of them are gone, so 8 of them are left.
Yeah.
Okay, so I have 8 distinct objects, but how many distinct locations? 3. So that is this problem now. So I don't need to count them again one by one. I would say that, okay, in total, the number of ways that I can fill up all of them is P, 8, and 3. Yeah, is that understandable?
Yeah.
So of course you can do it again case by case. You can just completely forget about today's lesson and use the product group to answer this one. I prefer you to learn to use this formula. Okay? So then what is the final answer? Can you tell me what's the final answer? What should I do with these numbers? I don't care about calculating this number because I hope that you can do it yourself. So I should multiply it. So I should multiply them. So the answer is 5 times P, 8 and 3 times 4. But multiplying 5 by 4 is simple, so I prefer to write 20, but I don't bother to calculate this one. Of course, if you want, you can calculate. So that's the final answer I expect you to answer for this problem. So you see, again, I am using this lesson is in a combination what we learned before and what we learned before. Any questions? Yes?
Don't the numbers in the middle also have to be distinct as well?
No, they are distinct, yes.
Are they?
No, what do you mean, are they? I myself want to choose them distinct.
I mean, but okay, if we, for example, take the second square, and if we have 8 options left, would that mean in the third box that there are only 7 options left? Because it can't.
Oh yes, you can. The way that you are counting is starting from scratch.
Okay.
But the whole point of today's lesson is that I don't want to look at them individually. I can count the number of ways for filling up these locations directly. The way that you are counting, yes, you have to start writing, I don't know, 2 of them are gone, how many of them are left? 8, and then you say 7, and then you say, I don't know, 6. If you solve it in that way in the exam, that's okay, but instead of writing it 8 times 7 times 6, I wrote P, 8, and 3. If you calculate P, 8, and 3, it becomes exactly the number that you mentioned. Yes? That's what I'm saying. I want you to make you ready for the next coming lesson. So I want you to think about it in this way. Any questions? Okay, so if you don't mind, let me just wait a little bit. No, that's also a simple problem. So how many ways can 5 students be chosen from 15 and be seated? Okay, and seated in 5 numbered chairs? That's also simple, isn't it? So how many distinct objects I have? I have 5 students, and I have, oh, by the way, okay, so that's a little bit different. So 5 students and 15 chairs. So how do you think about the problem? Okay, let me first solve this problem. Let us assume that we have 15 students. Student number 1, student number 2. This is different from the problem here. Student number 15, and I have chair number 1, chair number 2, up to chair number 5. Okay, so momentarily forget about the problem. Let us assume that I have 15 students and I have 5 distinct locations. Okay, how many ways I can let these students, of course not all of them can sit, but I choose 5 of them and arrange them in this way. So how many ways I can do that? P of 15 and 5, yes? So the answer to this problem is P and 15, P of 15 and 5, yes? Is that understandable? Because I have 15 distinct objects, here are humans, and here we have 5 distinct locations. They are chairs labeled from 1 to 5. So the number of ways that I can arrange this is this number, exactly according to what we studied. Now, this problem that I expressed here, the number of students are 5, but the number of chairs is 15. Okay, so now my question is that how we can do this problem? How can, in how many ways we can do this? Of course, there are many chairs left empty this time. Yes, for example, I can send the students from 1 to 5 to chairs from 1 to 5, or I can send the students from 1 to 5 to chairs from 10 to 15. Yes, but I can also, I don't know, send student 5 to chair 1, student 2 to chair 9, and something like this. Okay, in how many ways I can start arranging it? Yes?
Isn't it the same way as the first one?
Yeah, it's the same number. I don't know, from psychological point of view, for us it's a different, because probably we feel that we are better than chairs, or I don't know, we give a role to us more important than the roles of the chair, yes? But from mathematics point of view, they are the same, yes? So there is no difference. I hope that you understand that, yes? So this is P, 15 and 5 again. So, by the way, if you don't still understand that, you have doubts about it, how can we solve the problem? I can say that, okay, for chair number 1, how many options? A student number 1 has some choices in front of him. How many choices student 1 has? 15, yes? But after the first student made the choice, for the second student, how many choices are left? 14, yes? And then for the third one, there are 13, and then for the next one, we have 12, and then eventually we have 11, yes? And this is exactly this number, because if I ask you to calculate this number, it is just 15 factorial divided by the difference between them, which is 15 minus 5 factorial. And if you calculate that, it becomes 15 factorial divided by 10 factorial. I hope that you agree that this number is exactly that number, yes? Because instead of 15 factorial, I can write 15 times 14 times 13 times 12 times 11 times 10 factorial, and this 10 factorial and that 10 factorial are gone. So this is a good lesson to have in mind. So it doesn't matter if the number of objects is less than the number of locations, or if the number of locations is less than the number of objects. If you want to arrange them, the answer to both of them are the same. Yes?
Why is it not P 5 and 15?
No, this is it's not possible. In this notation we used, we bring n first and r second. Yes? So we do not have, for example, we do not have P2 and 5. by definition of that symbol, the symbol is n objects and r locations. Yes. If you think in the way of objects and locations, you get confused. You think that you have to switch them. No, P, N, and R always refers to the same number. So whenever someone asks you what is this number, it will tell me this number, first of all, makes sense if the first number is greater than the second number. You do not have this situation. This is meaningless. Yes? So whenever you see this refers to this number. Okay? But I'm just, because when we started teaching about this, we set up this for this situation. But then I changed the situation. You might think there is a distinction between this new situation and the previous one. I try to convince you, no. From mathematics point of view, now the objects are humans and the locations, no, the objects are actually chairs and the locations are humans. They are putting chairs on top of human heads, yes? But that's something like that.
Yeah.
Okay. So let us go to this. Okay, that is exactly what I wanted to mention in this remark. So let R and N be natural numbers, yes, such that R is between 1 and N. As the last two examples, I should say two examples show the number of ways that one can choose R objects out of N distinct objects and arrange them in R distinct locations, and the number of ways that one can arrange R distinct objects in N distinct locations are both equal to Pn and R. So I just want you to understand, it doesn't matter how we can solve it. If I want to explain it once more, so what we have, so let us say that I have 3 objects, A, B, C, but I have 5 locations. 5 locations. And now assume that I have 5 letters, but I have 3 locations. Yes? If I ask you in how many ways I can pick up these numbers and arrange them in these locations, of course, in this case, some locations are left empty. Yes? And in this situation, some of the objects will not find the location. But the number of ways that I can solve that problem and the number of ways that I can solve this problem are both the same. And the answer to both of them is P. The bigger number here is 5, the smaller number here is 3. So the answer to both of these situations are the same. Yes? I want you to have this in the back of your head when you want to solve the problems. Is that clear? Because I want you to understand that, because the next example relies on your understanding of this remark. Okay, so let us go to this problem. Using the letters in the word magnetic, how many 5-letter words can one write down such that in each of them both letters M and N are used? M and A are used. I want you to think about the problem yourself. I don't want you just use the product rule. Of course, you can use the product rule and solve the problem correctly, but I want you to try to use this symbol P, N, and R that we learned about it today to solve that problem. Let me give you a little bit of time. Okay, do you have the answer? No? Okay, let me first of all, what are the important things that you really care here? So first of all, I see if these objects are distinct. In this case, yes. In a combinatorial problem, that's important. So I have letter M, and I have A, G, N, E, T, I, C, S. So it is extremely important to first understand that all these objects are distinct. The second thing that is...
It's just magnetic.
Oh, sorry. What?
It's just magnetic.
Oh, okay, so I can clean this, thank you. So this is magnetic. So I count them, 1, 2, 3, 4, 5, 6, 7, 8. So the first thing is important for me is that the objects are distinct. The second thing is that how many of them are there. Yes, so the total number is 8. Now I want to write 5 letter words. If I just stop here, what's the answer? How many 5 letter words I can write? P of 8 and 5, yes? So if you want, you can calculate. But in this case, how many locations I have in general? I have 5 locations. Okay, but I have some constraints. I want to use M and A in all of them. Okay, so how do you do that?
I was thinking, first you can take all of the combinations where you use all 8 letters, so that would be P85 as mentioned before, and then you do minus P6 and 5, because those would be all the combinations where M and A are not used.
Is that right? No, but the way that I don't think it's correct. Okay, let us, by the way, that's good to analyze. So, okay, any other suggestions? No, because if you want to use the complement, you are using the complement principle. So you have to be very careful. Yes, I will tell you why. I think that is not correct. We will check it out, yes?
You have 5 positions, and 2 of them need to be used for M and A.
Yes?
And all the possibilities for these, there are five positions.
Yes?
And since M and A are distinct from each other,
Yeah.
you can just put down that there's 5 possibilities for M to be placed and 5 for A to be placed.
Yeah. So that's exactly related to the problem that I just told you. Yes, here. So that's correct. So how many locations we have? We need 5 locations. Yes. So 1, 2, 3, 4, and 5. Okay. So we need 4 locations. And then we know that A and M should be used. Okay, so the number of objects I have in this case is 2. The number of empty locations that I have is 5. But we just learned before that it doesn't matter if the number of objects is less than the number of locations or the number of locations is less than the number of objects. Yes, so I would say that the way that I can choose M and A and arrange them in these 5 positions is, as Gustav mentioned, just P5 and 2. Yes? So what I have done so far, it means that I have labeled 2 of these locations and I have arranged A and M there. I have considered all of them. The choices of my locations, the freedom in the choices of my locations, and the freedom in arrangement of A and M, both of them are considered in this one single formula. Yes? Okay, so now 2 of them, 2 letters are gone, and 2 locations are gone. And then how many locations are left for me? 3. How many letters are left for me? 6. So then in how many ways I can fill up the locations with the letters? In this case, the number of letters is more than the number of locations, but it doesn't matter, yes? So this becomes P of how much? 6 and 3. And then what are we supposed to do with these 2 numbers? Multiply it. Yes? Yes?
Why isn't it 8?
What?
Why isn't it 8?
Oh, because this is the way I'm counting them.
Well, you can repeat n, right?
No. I told you that this is a convention in combinatorics. When I say use the letters in this word, if there is no repetition in the word itself, you're not allowed to do the repetition. Yes? Okay, so this is the number of ways we should do it. I mean, it is better to calculate the final number so that I can compare with you what you said. If the answers are the same, then we need to learn why they are the same, okay? So what we are doing here, let me calculate that. If I ask you to calculate that, you write 5 factorial. What should I write in the denominator? 3 factorial. And then multiplied by here, I should write 6 factorial. And in the denominator, again, I have 3 factorial. So let me calculate that. Instead of 5 factorial, I write 5 times 4 times 3 factorial divided by 3 factorial. Instead of 6 factorial, I do something similar. 6 times 4 times 4, 6 times 5 times 4 times 3 factorial divided by 3 factorial. Now, what is happening this time? This 3 factorial and that one is gone. This one and that one is also gone. So how much is that? This is 20, 20 is 400, 204, 2400, yes? Am I right? So this is the number of ways we can do this. But what you said is what?
It becomes a lot bigger.
But I want we understand why this is going to be wrong. Okay, so what you said is we calculate the whole thing, which is P8 and 5, and then you take the ones that does not contain M and A. Yes. So in that case, how many ways? I have only 6 letters left, and I have how many positions? 5. So what you write is 6 and 5, something like this. I don't know, have you calculated this yourself?
Yeah, it was 6,000.
So this becomes 6,000. Yes, it's much bigger. Yes. Yes. Why do you think this is the case? So what he is telling, he is counting all possibilities that I can make a 5-letter word out of these letters. That is correct. Yes? And now he is saying that, okay, by this number, I mean the number of letters, the number of words that I can make does not include neither A nor M. Yes? And he is subtracting this number from that number. According to him, the answer is 6,000, which is completely different from this answer. But why do you see, what is the flaw in this argument?
Could it be that it doesn't specifically have to or be M and A?
Yeah, so you are taking both M and A out.
Yeah.
But there are some words that include A, but not M. You should also take them out. And there are some words including M, and not the other way around. You should take them out. By the way, that's also good practice. Let us count them. Yes? Let us see, finally we can get the answer right. But I hope that you understand this is not correct. You took the number, the words not including M or A. So both of them, you exclude A and M simultaneously, okay? But how should I do that correctly? I need to subtract more. I need to subtract the letters, the words with consisting M, yes? But not consisting A. So what are the number of those numbers? Can you tell me? The number of words containing M and not containing A. For M, how many locations I have? I have 5 locations for M. When I put my M, there are 6 of them left for me, and how many how many positions I have? I have 4. So, and then I have to multiply it by 2, because the same reason can hold for A. Yes? And if I calculate that, it becomes 10 times this number, which is 6 factorial divided by 2 factorial. So how much is this number? It's 3,600. Okay? And 6,000 minus 3,600 is exactly 2,400. So that's also correct. If you want to use the complement rule, you have to solve it harder, but it works. Is that clear? So what I did, I would prefer this solution. And in the exam, if I don't insist you to give the final number, this is correct. That is the final answer to this problem. You just stop there. But if you insist to use the complement rule to solve the problem, this is the total number of words that I can make. This is the number of words excluding both A and M. These are the number of words excluding only A. And I multiply it by 2 because I also want to count the number of words excluding M as well. And then I take it away from this one. What is left is again this number. So if you insist to use the complement rule, you have to do it in this way. Understandable? Okay. So this is the last example. I want to wait a little bit for you to solve that problem and then we are done. Yes, I think so, yes. Today, the take-home lesson for today is actually to learn that it doesn't matter if the number of objects is less than the number of locations or if the number of locations is less than the number of objects. Okay, so how many permutations of the letters of the word second are there such that the vowels are in even locations, So if I want to have second, how many letters are there? So 1, 2, 3, 4, 5, 6, all of them are distinct, so it means that I need 6 locations. Let me make it faster. So this is location number 1, 2, and 3, 4, and 5, and 6. Yes? Okay, so this is location number 1. What is happening? Okay, location number 1, 2, 3, 4, 5, and 6. Yes? So the even locations are number 2, number 4, and number 6. So I want to put the vowels, which are in this case E and O, in 2 of these 3 locations. Yes? And the order matters. So here the number of objects is 2, the number of locations are 3, but everything is as before. So the answer to the first stage is how much? P, 3, and 2. Yes? After this is done, this is important for me to tell me what is the second one. Now assume that E and O are located, 2 of these locations, and then we want to arrange the other letters in the ones that are left. So how many of them are there in how many ways? Yes, Aaron, you want to say?
P of 4.
P of 4? No. Because, what is your answer? 4 factorial. Because in this case I have how many locations left?
But that is 4 factorial.
No, you told me 4, 3.
4, 3.
That becomes 4 factorial.
Yeah, that's correct. But how did you come with that answer then?
Because
So what is playing the role of 3 here?
4 objects in 3.
Decisions.
Ah, yes, that's correct. That's correct. Yes. Yeah, that's correct. So you told me 4, 3, yes? Exactly. That is working. But 4, 3 is also 4 factorial. Yes? So you can come up to this answer with this idea, or you can just say that, okay, how many locations are left for me? 4. And how many objects I have? 4. So I use 4 factorial. Yeah, that's correct. But if you write that, that's completely correct. So that's the answer. Any questions? Okay, so we'll stop the lesson here. Thank you.